Hello everyone, we are Team Raptors PL, a team of young engineers and space enthusiasts from Lodz University of Technology in Poland. Together, we are developing our most technologically advanced project, Rover Rex 2.1. To create such a machine, the team was divided into 5 main fields. Mechanics, responsible for modeling, production and overall construction of every mechanical part of the rover. Electronics, who design and assemble our own custom PCBs. IT, which consists of ROS, computer vision, AI and embedded systems programmers. Science team, that performs required research of the rover's mission environment and gathers samples in search of possible signs of extraterrestrial life. And the marketing team, responsible for our advertisements, sponsorships and budget. Additionally, to manage such a huge and challenging project, our organizational structure was divided by so-called products, which are the most crucial subsystems of the entire rover system. These products are manipulator, a special robotic arm designed to grab and manipulate objects like rocks and switches. Science module, which role is to gather soil and surface samples which will be examined by our scientists. Rover body, chassis that protects the internal components of the rover. Drive system, allowing smooth and reliable vehicle movement. Autonomy, developing AI and machine learning solutions that allow the rover to operate independently without being controlled by humans. Simulation, preparing virtual environments in which we firstly test our solutions. Power, responsible for energy delivery to every electronic component of the rover. Drones, which support the mission of our rover from the air. Every of these products has a special leader called product owner, which distributes tasks along the team members and coordinates their workflow. The project manager is responsible for contact with the product owners to support and supervise their work. To allow easier management, we introduced a project management software, Open Project, which provides work scheduling and tracking, Gantt charts, Kanban boards and time tracking. We want to participate in the European Rover Challenge 2026 to test our engineering and construction skills in harsh environment and simulated space missions to conquer the Mars at the Lodz University, so that one day our technologies are put on the real flight to the real red planet.
The Rex is powered by up to 3 6-cell LiPo batteries, each capable of powering the rover on its own. Every pack includes a custom BMS that protects against overcurrent, over and under voltage, temperature limits, short circuits, and cell imbalance, disconnecting the pack if needed. The BMS also provides full telemetry for state of charge and state of health estimation available to the operator. A custom hot swap system allows for quick exchange of batteries, regardless of the charge, without any interruptions. It also includes safety relays which disconnect all batteries via the red stop button. Additionally, the black stop button isolates all actuators. A bright WRGB status indicators provide clear visual feedback of the system state, even in the bright sunlight.
The Rex 2.1 suspension was redesigned for higher reliability and safety. A differential bar mechanism improves terrain adaptation and maintains traction, while a second pump increases pneumatic redundancy. 2 reused motors were integrated after removing their cases. Front and rear actuators are independently controlled and work with the IMU to keep the rover level. New side connectors allow quick disconnection during servicing and provide mounting space for the suspension pump, valve drivers, and the safety indicator driver.
In our rover, we implemented 3 types of kinematics, which include the typical Ackermann steering, but also a crab-like kinematic mode, allowing us to drive the robot sideways. What's more, the spinner mode lets us rotate the rover in place. In terms of communication, the rover and base station exchange data through a point-to-point wireless link, and if that link breaks, they switch to mobile internet using a secure tunnel. All messages are sent using MQTT, and this year we improved security and added message validation, so everything stays safe and sound.
The manipulator is designed for a wide range of mission-critical interaction tasks. Its 6 degrees of freedom structure provides high flexibility and large workspace, while the mechanical design prioritizes simplicity, durability, and easy maintenance. The arm lightweight or rigid aluminum profiles, and mechanical components for an optimal strength-to-mass ratio. The drivetrain uses geared DC motors and linear actuators selected for high torque load capacity and efficient force transmission with minimal backlash.
The science module consists of 4 main parts. First, being the rock scale, which is mounted on the side of the rover and is used to weigh heavier samples collected by the manipulator. Then we have the drill, mounted on the back of the rover. It's used to collect samples from deeper parts of the surface and deposit them into rotary, just below. Then we have the rotary module, which is rotating in place just so we can settle right under the drill and collect samples from it to keep them for further analysis. Last but not least, we have the surface sampler module. It is a vacuum mounted on the front of the drill. Inside, it creates vortices. It's a cyclone system. The vortices cause the heavier particles like dust to settle down and go into containment, and clean air to continue through without the risk of motor contamination.
The drone is a custom-built quadcopter on a carbon frame, chosen for its strength, low weight, and foldable dihedral arms that improve passive stability. Its 500mm structure provides a compact, modular platform for onboard systems. Propulsion uses 4 BCS motors powered by a forest battery. Upgraded 60-amp ESCs improve reliability, noise suppression, and dynamic performance. Navigation is handled by the Hereford GNSS module with RTK corrections, enabling centimeter-level accuracy even in partially obstructed environments. Vision-based corrections further improve landing precision. Flight control is provided by the Orange Cube autopilot with redundant IMUs and barometric altitude sensing. Communication uses the CE MK32 system for RC control, video and data link. High-level logic and vision processing is run on a ground station laptop in MATLAB, simplifying onboard hardware while maintaining stable autonomous operation.